In today's lesson, we are going to put to use our idea of complex numbers and how they work in relationship to more with the root work, but also with just equations and what do we notice about them. So pause the video for a moment, please, and go ahead and find the roots of this quadratic. So this is based on what we did yesterday. Please note you can't factor this, so therefore you're going to have to do the quadratic formula. Obviously, we're not going to tell you that all the time, but go ahead and do the quadratic formula to find the two roots, please. Therefore, in order to find the roots, it's x equals the opposite of b, plus and minus the square root of b squared minus 4ac all over 2a. So therefore, x equals 4 plus and minus the square root of 16 plus 36, again, be careful with that part, all over 2. Which then gives me, minus 36, sorry about that. Which then gives me 4 plus and minus the square root of negative 20 over 2. So remember how to break down square roots. So we know that negative is the same thing as negative 1 times 20. Negative 1 is I squared. And the square root of that is I. And then that's the square root of 20. Now we have to break down 20. So remember how to break down radicals. This is from back in chapter 2. 20 is 4 times 5. We always try to get 1 to, well, we have to get 1 to be a perfect square. So again, we're looking at what two numbers multiply together. So therefore, back into my problem here, we have 4 plus and minus 2i times the square root of 5. And then that's all over 2. Again, we did the work of breaking down radicals early on, back in quadratics, back in chapter 2. But it's not something that we do very consistently. So make sure that you're really careful that is multiplication. Some of you, when you see this, will go straight to this is I times the square root of 20. And that's perfectly fine. To get that negative out from underneath there, we know that's an I in front. This is just the why it is what it is. But there's nothing wrong with just going from straight here to here. But you do have to break down the square root of 20. And now lastly, I have to simplify this. So I can factor out a 2. I talked yesterday about just simplifying, like dividing them each by 2. Otherwise, really what you're doing is you're factoring out that 2. And then the 2 over 2 simplifies out. And that's why you get 2 plus and minus I times the square root of 5. What you just find. We asked you to find the roots. And the roots are the values of x when y is 0. So we set y equal to 0. And then we solved. And these are our two roots. 2 plus I times the square root of 5. And 2 minus I times the square root of 5. Also, just take note, you'll always notice I put the I in front. That way it doesn't accidentally look like it's underneath here with the square root. So, nice little practice from what we did yesterday. So in today's work, we're going to keep working with these complex roots and then looking at more specifically complex numbers. So find the roots of the quadratic function by solving for x when y is 0. We did the first one as our warm-up because it was very similar to what we did yesterday. But now what I want you to do is I want you to solve this one as well, and then do the graph of either of these functions intersect the x-axis. Please note for this one, it is absolutely fine if you square this whole thing out. Remember, if you square the whole thing out, it's x plus 5 times x plus 5, expanding that through. Otherwise, try instead to undo the operations. This form is actually easier than the previous one. So pause, go ahead and solve this, make y 0. So therefore 0 equals x plus 5 squared plus 9. So solving, we subtract 9. So we have to undo that square by square rooting. Keep in mind, when we undo a square by square rooting, it's both the positive and the negative. So now square root of negative 9, that's I times the square root of 9, which is 3i. So therefore, positive negative 3i equals x plus 5. Lastly, subtract the 5 on both sides to get x by itself. If I would have expanded it out, I would have gotten a quadratic, and then would have had to do the quadratic formula. Then I would have had to simplify down that radical. When it's in this form, when it's in graphing form, this is much easier to solve. So those are my two roots. Do either of these cross the x-axis? No, these are not real numbers. These are complex numbers. So please keep that in mind, that neither of these will cross the x-axis. So now, what do you notice about the complex solutions in 79 and then the warm-up? Describe any patterns you see and write all observations. So what I want you to do is I want you to take a look at these two sets of solutions and just jot down what are a few things that you notice between the two of them. So hopefully one of the things that you talked about or noticed is they both have the exact same first term. They both have the exact same last term. The difference is the sign, and that works for both of these. Sign is different, everything else is the same. Because these are called complex, that's the new, conjugates is old. You know that already. Oop, I didn't spell that right though. Those are called complex conjugates, where the negativity in the I changes. So we did conjugates in the past. Now these are just with complex numbers. So we're going to look at these four pairs of complex conjugates. See how the first term is the same, the last term is the same, one's a plus, one's a minus, so that's for all of them. So for this problem, what I want you to do is I want you to look for patterns as you calculate the sum and product of each pair of complex numbers. So for sum, you're just going to add the two together. For product, if you need to do the area model to help yourself out, please feel free to do that. Just keep in mind, simplify any I squareds. I squareds do need to simplify. So go ahead and do the sum for each of these four and do the product for each of these four. And then I want you to look at what kind of patterns do you notice? What do you notice about these? So check your answers. I'm going to do, or below here, I have this one, the product for that one listed out, at least that way in case you messed up any of the products, you can follow this bottom one through. So I set each of them up, 3 plus 5i and 3 minus 5i. I did the area. Don't lose your negative signs. So then from here, once you have I squared, you know I squared is just negative 1. And it's just multiplied because it's right next to it, so it's multiplied by it. So that becomes 9 plus 25, which is where that 34 comes from. Okay, so look what happens when I add two complex conjugates. Every single time, my i's dropped out. And that's the part of it. One is a negative 5i, one is a positive 5i. So my i's are going to drop out when I have complex conjugates. My product, what was really nice with these, is these middle two terms in the middle here, one's positive, one's negative, which is why the i's drop out. You just have the real number, and then the I squared, which you know is negative 1, which then changes that negativity. So just a few features to look at when we are adding and multiplying complex numbers. So with that in mind, what complex number can you multiply 3 plus 2i to get a real number? It's complex conjugate, 3 minus 2i. What happens when you multiply two complex numbers together? These are not complex conjugates. They are just two complex numbers. 16 minus 12i minus 20i plus 15i squared, which is 16 minus 32i. I squared, remember, is negative 1, which means that becomes minus 15. Lastly, that becomes 1 minus 32i. Anything special happen? No, I have a new complex number. It's not any kind of special complex number. It's just a complex number. So therefore, what complex number can you multiply generic form a plus bi in to get a real number? A minus bi. So those are the two complex conjugates that are just generalized. That's why we say complex numbers are in the form a plus or minus bi. So what we're going to now work on is we're going to create a quadratic equation based on knowing two of the roots. So if we know two roots like we did before in that table, we should be able to write an equation for it. So it's kind of going backwards with it. So Austin had an idea. He knew that if 3 and negative 5 were solutions of a quadratic equation, then he knew that x minus 3 and x minus a negative 5, which is x plus 5, would be factors that could be multiplied together to get a quadratic polynomial. So I want you to think about that. So if you had a 0 of 3 or a solution of 3, its factor then would be x minus 3. Because if it's a solution, it would be x minus 3 equals 0. I add the 3 over. That's how I get x equals 3. But then I also know that if negative 5 were a solution, its factor would be x minus a negative 5, which of course simplifies into x plus 5. And then if I multiply these two out, I get x squared plus 5x minus 3x minus 15. So my quadratic equation with those two solutions would be the following. But can't we just do the same thing with complex solutions? So this is how it works with real numbers. It's just x minus whatever it is. Now let's take a look at it with complex numbers. So let's use the pairing. Let's see, what did we have? Let's use what I had just worked on before, 3 minus 5i and 3 plus 5i. So those are my two solutions. Those are my two, in essence, roots. So if I know my roots, I should be able to find my quadratic. When my root was 3, it was x minus 3. Now my root is 3 minus 5i. So now it's going to be x minus my root. Okay, now I know I have parentheses and parentheses, still totally doable. And then before it was minus 5, so it was x minus a negative 5. Well, here it's going to be x minus this root. What might make it easier is just to go ahead and send through that subtraction sign. That way you can then go ahead and multiply them together. And that is my recommendation. Send through your subtraction. That way I do not have parentheses within parentheses. Be super careful and make sure you distribute through that negative sign. And now if you want, go ahead and draw the area model if it makes it easier for you to expand. So x times x. Why don't you pause this and go ahead and do this and check your work. So x squared minus 3x minus 5xi minus 3x plus 9 plus 15i plus 5xi minus 15i and then minus 25i squared. I'm running out of room. Minus 25i. Oh, come on. I squared. Let's see. I should have 9. 3 times 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Okay. Now I just go through and simplify. So what I'm doing right now is I'm trying to find my quadratic equation. So therefore, I have an x squared. I only have one of those. And then I have a negative 3x and a negative 3x, which is negative 6x. And then I have a negative 5xi and another positive 5xi, so that's 0. And then I have a 9. And then I have a 15i and a negative 15i, so that's 0. And then I have this minus 25i squared, so minus, and I know 25, and I know I squared is negative 1, which means it's x squared minus 6x plus 9 plus 25, which means my quadratic is x squared minus 6x plus 34. That's the quadratic equation that has those two roots. Fantastic. So if you know the roots, you can write the equation. And remember, you know complex roots. They really come in pairs. Complex conjugates. If one's a minus, the other one is a plus in terms of the imaginary part to it. So what I'm going to have you do is the same type of problem, but I'm going to pick a different one. So how about I'm going to have you write the equation that contains the following two roots. So go ahead and write the quadratic equation that contains both of those roots. Go ahead. Okay, so if this is a polynomial, we can put y equals, and then we have our equation. So now, if you know the quadratic, you can find the complex roots, and if you know the complex roots, you can find the quadratic equation. And we can do this with cubes and 4th degrees and 5th degrees. We just have to do it for each of the sets of roots. But please, please remember, if you have complex roots, they always come in pairs.